All right, so I've been excited and alluding to this video for a while now. What happens what happens graphically with inverse functions? So we're going to start by doing a little exploration with the examples from the most recent video. So in the most recent video, we looked at 3 functions and we found their inverse functions. Let's look at the more interesting ones. 2x plus 1 divided by x minus 2. That was one of the functions we looked at. Let's look at its inverse function. Its inverse function we found was, I don't remember actually. Its inverse function was 2x plus 1 over x minus 2. Wait a minute. How did I not comment on this before? Its inverse function is itself. It is its own inverse function. I wasn't even paying attention. All right. So what we're going to talk about is symmetry. Notice that this blue graph is the same. Tilt your head a little bit. This blue graph is the same to the left or above the diagonal line as it is on the right of the diagonal line. That's why its inverse is equal to itself. Another thing that we looked at was y equals x plus 5. Its inverse was y equals x minus 5. And look again, the blue graph is just the reflection of the pink graph across that diagonal line. Let's look at the other one that we did. We did 3x cubed plus 3. And we said the inverse was the cubed root of 1/3 x minus 1. Remember, you can write the cubed root as a function with a 1/3 exponent. Oh, look at that. Again, it's like the same thing. Can I rotate myself 45 degrees? I can rotate myself 90 degrees, but that's too much. I thought it'd be really great to rotate myself 45 degrees and then I wouldn't have to keep turning my head, you know? But yeah, maybe this is a little extreme, I think. All right, something to figure out for another time. But notice, right? The blue graph is symmetric to the pink graph on that diagonal line. That is what inverses look like graphically, which is really cool. And again, we can also think of inverse functions as switching x's and y's. This point on the main graph, if you switch that x value and the y value, is this point. This point on the main graph, switch that x value and that y value, right? The x of 0 becomes the y of 0. The y of 3 becomes the x of 3. And any point you pick on these functions, you switch the x coordinate and the y coordinate, 1, 6 should be 6, 1. Oh, look at that. Switch those x's and those y's. All right. And that's what we've got going on here. So I got a little challenge for you. And this is like one of those video game challenges, like where it's a boss fight. The boss is so hard. You're like, how am I supposed to win this fight? And turns out it's impossible and you're supposed to lose. That's the kind of example I have for you. Example 5. Try to find f inverse of x, where f of x equals x squared. If you succeed, you're doing it wrong, okay? Because it's impossible. So let's look at this. How do we find inverse functions? Well, we write it in terms of y. This is our original function. Then if we switch the x's and the y's, this is going to be our inverse. Well, now we need to solve for y, so we take the square root of both sides. But whenever you take the square root of both sides, you need a plus or minus. Because there are 2 values of y that when you square them, give any given x. Right? Y could be positive or negative 2, and it squares to become the same result. That's where this plus or minus comes from. And you say, well, Jason, you said this was impossible. What's the problem? The problem is that this is not a function. I'm not even going to write it as f inverse of x because it's not a function. Look at what this looks like. X equals plus or minus square root of 1/2. So here, let's do it down here. X equal the positive square root or the negative square root. This is the function that we just found. But remember back to what it means to be a function. One input should only have a single output. We're getting double outputs everywhere. It fails the vertical line test. It fails the vertical line test badly. Well, what was the original parabola that we were trying to find an inverse function for? Notice we still have that symmetry, right? We still have that reflection. The blue graph and the green graph are the same thing, reflected over that diagonal line. But the problem is green graph ain't no function, all right? So what we're going to talk about next is how to figure out if a function has an inverse. Well, green graph is not a function because it fails the vertical line test, and there's some sort of reflection going on. That's going to bring us to something we call the horizontal line test. Because essentially, for a lot of these inverse functions, we're just reflecting them sideways. So if something fails a horizontal line test and you reflect it sideways, it's going to fail the vertical line test. Okay? So let's introduce that more specifically. All right, definition. Whoa. Definition. If a function f, let's phrase it differently. If there is a horizontal line that crosses graph of f at least twice, then f is not 1-to-1. So that's our definition. F is not 1-to-1, and f inverse is not a function. Okay, this is known as the horizontal line test. And the reason why, let's abbreviate this, I'm never writing that many letters again, HLT. The reason why it has to do with that kind of reflection thing that we have with inverse functions. So let's try to use a horizontal line test. Example 6. Oh, also, I love abbreviations. 1-to-1 is often abbreviated like this. 1-1. Excuse me. Why am I so burpy today? I had a breakfast burrito. It was pretty good. I don't think there's a correlation with breakfast burritos and burps though. But if you know more about burps than I do, please let me know. Do the following have inverse functions? And there's kind of two common ways of saying this. And these are both of them, right? Do the following have inverse functions? Or f inverse is not a function. These mean the same things. Okay, just different phrasings. So let's look at some graphs. I'll just plot some for you. And as I'm plotting these, try to come up with an answer. Look at these, think about these, decide whether These are going to have inverse functions. And the answer goes back to the horizontal line test. First problem, yes, it does. It passes the horizontal line test. Second one, nope. There's many horizontal lines that this one fails. It does not pass. Third one, nope, does not pass. Again, there's a bunch of different horizontal lines you could draw. The fourth one, that's our reciprocal function. This does have an inverse. In fact, its inverse is also itself. This first one is a toolkit function, right? This first one's the square root of x. Let's look at a couple more. E, reciprocal squared, also a toolkit function. Nope, fails a horizontal line test. Let's look at one more. Absolute value function, also a toolkit function. Nope. Fails a horizontal line test. And again, by these red lines, these are just examples of some horizontal lines that show that it fails that test. If you can draw a horizontal line that crosses the graph at least twice, then it does not have an inverse function. It is not one-to-one. So no is the same thing as saying not one-to-one. Yes is the same thing as saying yes, it is one-to-one. Having an inverse function and being one-to-one means the same thing. All right, let's do another example. More graphing information. Example 7. Given the following graph, I'm going to ask you some questions. Let's get out the graph paper. I love how I can just click and immediately my paper turns into graph paper. I'll give you the function with these points, and it's a line. One of the nice things about teaching with technology is I can draw a perfectly straight line. I can't do that in class. In class is what my lines look like. All right, so given this function, this is f, answer the following questions. What is f of 1? So again, this is like before, that example with the table. Same solution, just now it's graphical. X is our input, and we're looking for a y. So what point has an x coordinate of 1? It's this point, which happens to have a y coordinate of 1. Okay, we could do that again for part B. Find f inverse of 1. Sorry, f inverse of -1. We don't have f graphed, or we only have f graphed. We don't have f inverse graphed. So in order to find it from the graph of f, we think about this as a y coordinate. If there's a y coordinate of -1, what x coordinate gives that to us? This is the point on the graph with a y coordinate of -1. What's the x coordinate here? X coordinate is 0. So that's how we can find information about f inverse given only the graph of f. Find f inverse of 3. Let's do it again. It's the same logic, right? We can do this by looking at when is the y value equal to 3? Y value is equal to 3 right here. What's the x coordinate here? And the answer is 2. That's how you can solve these problems. One more graphing example, and then we'll wrap up this video. Example 8. And I want you to graph f inverse of x. Ooh, this is a little new. Oh, not like that. And here I'll give you the function. Function starts right here as these points. And then this is one of those square root graphs that I'm really bad at drawing. It looks something like this. This is our function f. So to graph f inverse, all we do is switch the x's and the y's. Look at the points on f. What are these ordered pairs? Well, we have the ordered pair -3, 0, -2, 1, 1, 2, and 6, 3. So f inverse should just be what happens when you switch all those x's and y's. Switch the x's and the y's. Switch the x's and the y's. Switch the x and the y. Switch the x coordinate and the y coordinate. As soon as you can do that, just say, okay, f inverse is all about switching the inputs and the outputs, domains and the ranges, inputs, outputs. I think I've already said that. X's and y's. However many ways you want to phrase this, that's f inverse. Well, now let's plot these points and see what happens. 0, -3, 1, -2, 2, 1, and 3, 6. 1, 2, 3, 4, 5. Oh. And then we connect it in the same shape. One way to check our answer is look at the diagonal line. Look at this perfectly diagonal line, not that one. Look at this perfectly diagonal line. Is the white graph the same as the red graph, just reflected about the yellow line? That diagonal line y equals x. Close enough. You know, Jason didn't draw it quite well. I need to rotate this camera 45-degree angles again. Yeah, it's close enough. Here we go. Red graph is f inverse of x. And we're done. You know, I tried to salvage that. I'm going to write my f again. Let me know if you have any questions.